안녕하세요. Good morning, everyone. Thank you for coming to this talk. Today, I'm going to discuss the topic, big models without big data, using deep networks for computer vision in data-scarce settings. So this is the work of many people in my team at Naver Labs Europe, including John Almazan, Johan Cabon, César de Souza, Diane Larlus, myself, and Jerome Reveau. So what is the data scarcity challenge in computer vision? We know very well that supervised deep learning is state-of-the-art for many computer vision tasks, such as classification, segmentation, object detection, action recognition, and many more. But we also know that supervised deep learning requires really large amounts of annotated data. We know that the model which led to, let's say, the revolution in computer vision in deep learning required tens of millions of very well annotated data. But this, of course, is not always very easy to capture. But we do know that visual data is cheap and plentiful. You could imagine most people might think that computer vision researchers have it easy, right? They probably think of us as sitting down in this pile of images and videos because it is plentiful, right? There are lots of videos and images on social media, hundreds of millions being uploaded every day. And of course, we have a lot of visual data that comes to us from sources such as surveillance videos or even body cams and many other sources. But of course, for supervised deep learning, we need annotated data. We don't just need raw data, but we need to understand what is present in the image or in the video. But acquiring this data is expensive. Very often you have to go on Amazon Mechanical Turk or some other type of sourcing platform, which is quite expensive, and it's not easy to design these annotation campaigns either. Also, very often a lot of data is proprietary. So we know there's a lot of data out there. There's even a fair amount of annotated data out there, but it's normally closed source. Very often, the average researcher or the average developer doesn't have access to this type of high-quality annotated data. And in some scenarios, it's not even feasible. So imagine you had all the money to throw at this problem all the time. Sometimes it's just not possible. For example, if you want to collect information about optical flow, this, in most situations, is simply not feasible to collect. So given these challenges, how can we learn deep models without a lot of data? This is what I want to discuss today. So today, I'm going to describe to you 3 projects that were undertaken at Naver Labs Europe, which all addressed the problem of data scarcity in different ways. So I'll discuss these in sequence, starting with using domain adaptation, then using data cleaning to refine data, and then lastly, synthesizing data using virtual worlds. So let's start with the first, which is domain adaptation. Oops. So domain adaptation is a problem in machine learning in and of itself. It's quite a vibrant topic of research across many machine learning domains. So what is it exactly? The idea here is you want to leverage annotated data from some type of source domain, and you want to use models trained on this source data, and then adapt the models to a target domain of data which is similar but not identical. So to give an example, let's say you want to train a deep model to recognize the Golden Gate Bridge. You might have a lot of annotated data of RGB images, most likely. You might even have a lot of data of paintings. But let's imagine you don't have a lot of data of sketches, for example. So what domain adaptation can do is you can take a model that's been trained on this type of data and then adapt it via various techniques to be applied in this new source domain of sketches or drawings. So in our case, we use domain adaptation in the context of attention prediction. So what is the problem of attention prediction? What we'd like to do is to predict a topographical attention map over an image, some sort of RGB image, which represents the degree of attention that a human user would pay to every region in this image. So in the example you see here, you have an urban scene, and this sign attracts a lot of attention, as defined by this ground truth heat map or attention map. And what we'd like to do is to predict the same attention pattern that is seen in this ground truth data. And this is an actual result by our method. So how do most deep learning models typically address this problem? They would either model it as a classification problem. So for example, you might say, given a pixel or given a region, I would like to label it as either highly salient or likely to attract attention or not. Or you can simply directly regress to every value, every real value of your ground truth data. Our approach was to model attention as a stochastic process, taking into account the fact that we know that saliency is probabilistic, and then to use probability distribution prediction to get our predicted attention map. So to go into a bit more detail on our approach, we modeled an attention map as a generalized Bernoulli distribution. And what we aimed to do was to apply novel loss functions which are suited to the task of predicting distributions. And so these distance measures are used to define the distance or to measure a distance between two distributions. And so what we did is we used loss functions which are based on very well-known distance measures, such as the chi-square divergence or the Bhattacharya distance, and we used this to train our model. So our model in this case was a fully convolutional deep model, and we input an image, and then the output is this distribution. So it's a normalized distribution that represents a probability distribution. And we use the losses to improve the model. So this is the model, and now let's talk about the data. So how do we get data to train this type of model? So in typical models, supervised models for attention, you would normally collect data in the following way. So you would have a person sit at a desk and stare at a screen and look at images, right? One image after the other. And while they're viewing these images, there's an eye tracker which is mounted on the head of this individual. And this eye tracker is recording the movements of the eyes, which are calibrated with the screen. So this is a very accurate measure. The technology is fairly mature, but as you can imagine, it's very expensive to collect because these eye tracking devices are not cheap, and it's also very laborious. It takes a lot of specialized knowledge to be able to accurately calibrate the eye trackers. So as a result of that, most data sets for this task are quite small. So recently, in 2015, Zhang et al. Introduced a data set called Salicon, which used a very different and very interesting paradigm for describing attention and collecting data about attention. So rather than using an eye tracking paradigm, they used a mouse tracking paradigm. In fact, what they did is they asked the user to view an image that was blurred, and then to click with the mouse on regions of the image that they would like to deblur to have more information about the image. So you can see here that the user is presented with this image, and if the user clicks on a region, that region is deblurred. And what was quite interesting is if you look at comparisons of the same images with data collected using an eye tracker or data collected using mouse clicks, you can see that the pattern of attention is fairly similar across both modalities. There are some differences at times, for example in this case, but in general, they're really very similar. So our approach was to train our models, our attention models, using this Silicon dataset, and then to either fine-tune it and test it on a small amount of eye tracking data in our target domain. So here I'll show you some quantitative results with this approach. So first I'm going to show you results in the target domain. So this is training data and testing data in the mouse tracking paradigm. And here first you can see the comparison of different loss functions. And you can see that the loss function that was based on the Bhattacharya loss performed quite well in comparison to all the other methods. And so here you see some quantitative metrics, several of them. And you can see that our probability distribution prediction model does quite well on this task, outperforming the state-of-the-art methods at that time. So now let's look at the actual target domain. Because what we really want to do is to adapt our model from the source domain of mouse tracks to the target domain of eye tracking data. And so here what I'm showing you are results from two well-known but quite small eye tracking datasets, OC and VOCA 2012. And you can see that in both cases, our model performs quite well. In some cases, even without fine-tuning, meaning that if you take the model that was trained on mouse tracks, it actually performs very well on the model, on this data set of eye tracking data, even without adapting to this type of data. So to conclude, the problem that we tackled here is the problem of predicting visual attention, predicting maps of attention, and with a very limited amount of data due to the complexity of collecting this type of data in the real world. And our solution was to train with appropriate loss functions that have to do with distances between distributions, and then also to pre-train using proxy data in the form of mouse tracks. And here you can see some qualitative results with our method compared to the ground truth. And you can see that the method lends quite well to look at, for example, signage in urban scenes, and then also people's faces. So now I'll discuss the next approach to dealing with data scarcity. And this approach has to do with refining noisy data. So what is the context for this approach? The problem we wanted to solve in this case is instance-level image retrieval. So what is this problem? In principle, let's say we're given a query image, and we have a database, potentially quite large database of images. What we'd like to do is to compare our query image to all the images in this database, and then to retrieve only the most similar images in this database. So how is this typically tackled, this problem? This is quite a well-known problem, and with a long history in the community. And in particular, a lot of recent approaches have been trying to use deep learning and deep models for this task. One of the big advantages of using deep learning methods is that you can extract representation which is quite compact and efficient at testing time, which is very critical because, of course, we are searching through a large database, so efficiency is key. Some of the drawbacks, though, of these approaches were that they tended to use standard networks, which were originally trained for classification. So for example, you might take a network like VGG, which was trained on ImageNet. You might just cut off the last classification layer, and you will leave that untouched. However, because this model was not designed for retrieval, it's suboptimal. And the types of quantitative results you would achieve are tended to be significantly below the state of the art for this task. So we asked ourselves, can we learn to represent images for retrieval? And we found that the answer was yes, if the following three conditions held. So one, if training data that's appropriate is available. If the network architecture is able to capture the fine details that are necessary to solve this task. And if the training objective focuses on the actual task at hand, namely retrieval. So what was the challenge in terms of data acquisition in this case? So for this task, we focused on image retrieval of landmarks. So for example, these are typically buildings, famous buildings, for example, the Eiffel Tower or Big Ben, these types of landmarks. So to solve this problem, we looked for public data sets, and we found one which is fairly large scale. It contains about 200K images. And this was collected and released by Babenko et al. In 2014. So this is a data set containing 600 different landmarks. Some of the examples you see here. But one drawback of the data set was that it was quite noisy. And we found that if we use the data set as is, our models fail to learn effectively. Some of the noise you can see here. Let's say you're looking for this landmark. You might find simple misannotations. So very often you might have an image that was labeled with a category that's incorrect. And you also have cases of non-typical views of an image, of a landmark. So for example, if your landmark is a church, you might have an image of one door inside the church, which is not exactly relevant to the query. So how do we use this data? What we decided to do was not to throw it away, but to try to refine it and make it more useful. To do this, we proposed an automatic cleaning technique, which consists of the following steps. So first, let's assume we collect all the images tagged with a given class, with a given landmark category. We create a graph for this class, for all the images in this class, using a standard image matching technique based on key points. We prune the edges in this graph, where the edges correspond to similarity scores between images and nodes correspond to images themselves. And so when we prune this, we basically collect images, image groups or subgraphs which correspond to the same landmark. And as a bonus, because our initial matching method was based on key points, we were able to leverage these key point matches in order to extract bounding boxes as well. So this meant that, for example, if you have an image with a landmark in a sub-region, we can extract bounding boxes that allow us to localize the landmark within that image. And this sort of localization information proved to be quite useful in order to train our models. So with this approach, we were able to go from 4,000, 2,000, 200,000 images to 40,000 images with refined annotations. Also, we were able to collect approximate bounding box annotations for each of these, which resulted in a new cleaned data set, which is now publicly available for use. So one might think that we're dealing with the problem of lack of data, but yet we're throwing away hundreds of thousands of images. But what we found was that for the purposes of training this model, it was much more important to have a small set of accurately labeled images than to have a larger set of noisy labels. So that takes care of the data. Now the model that we actually used is, is the following. So we learned a representation of an image in the following way. We used a three-stream Siamese network, and we trained the parameters using a triplet loss. So what this loss seeks to enforce is the following. It takes in a triplet of images. So this is, for example, a query image. We have one image that's relevant to that query. So it's the same landmark in this case. And then we have a third image, which is an image of a non-relevant landmark or a non-relevant image. And what the triplet loss enforces is that the representation of the query image and the relevant image are closer in the embedding space than the representation of the query image and the non-relevant image. And so with this loss, this objective, we train the parameters of this model. So now I'll go through some of the quantitative results of this approach. And we're going to compare using several very standard data sets in the community. The first is the Oxford 5000 data set. So this data set contains 5,000 images of landmarks from Oxford in the UK. And then we also compared using an expanded data set of 105,000 images that contained 100,000 distractor images with no relation to the Oxford data set. We also compare using the Paris data set, which has 6,000 images of Paris landmarks. And we also compared lastly with the INRIA holidays data set. So here you see some quantitative numbers. Here you're seeing the results in terms of mean average precision for traditional methods. So these are methods that don't train the representation end-to-end, and they tend to be not particularly efficient, but they are very accurate for this task. And then on the left, you see some methods based on deep learning. So these, until recently, have performed on par or maybe slightly below par with respect to traditional methods. And then here you see the results of our method, which performs quite well in terms of mean average precision. And then also it has the advantages of deep networks in that it's quite efficient. So here I'm showing quantitative results on the expanded set. So this is searching for images in a database of more than 100,000 images. And you can see once again that the typical prior deep learning methods underperformed with respect to state-of-the-art, more traditional approaches. And the deep learning model that we propose does quite well in comparison. It's also interesting to note that the performance of our method degrades very gracefully when we add many more descriptor images. So here you're seeing results on the Paris 6K dataset and the INRIA holidays dataset. And you can see that the trend that we observe is quite similar. So now let's look at some qualitative results. So here I'm showing you some results on the Oxford dataset. And what you're seeing here on the left, highlighted in purple, is the query region of this image. So this really constitutes the only area of the image that's being used for retrieval purposes. And what's interesting to note is that with our method, we're able to retrieve relevant images at the top of the ranking, and also, taken from very different perspectives and very different scales. So to conclude for this section, the problem we try to tackle is how to perform efficient instance-level retrieval using deep models. And our solution was to train our models using reliable annotations and an appropriate model architecture. So the last approach to dealing with data scarcity that I'd like to address is the use of data synthesis. So what are the benefits of using synthetic data for computer vision? I think the benefits are probably quite clear to most of you. Given that we're synthesizing the data ourselves, it allows us a lot of control over what data we're collecting. Also, because we know and we're designing the environments and the scenarios ourselves, we can automatically collect annotations on what objects are present and where they are. And then also, we can produce a high quantity and variability of data. But of course, there are significant challenges. One is the chicken and egg problem. Very often, we need to understand and to use real-world data before we can understand what data we really need to solve this task. So the question becomes, can we really synthesize data without first collecting a fair amount of real-world data? That's one concern. Another concern is, how feasible is it to really synthesize data accurately and of high quality, and how cost-effective is it? Because we know that it's very expensive to acquire annotated data, but also it's not cheap to synthesize data either. We know that it's a fairly specialized field. We know that video game editors and animators are quite specialized in their disciplines. So our solution was to create virtual worlds using an off-the-shelf game engine, namely Unity, which was very accessible, we found, and fairly easy to use, and did not require extremely specialized knowledge for use. We also, to address the chicken and egg problem, to seed our virtual worlds with small amounts of real-world sensor data in order to improve the sort of real-world accuracy and the plausibility of the data that we're synthesizing. So some examples of the data that we use include not just RGB frames, but also GPS tracks of cars, vehicles, and then also motion capture data. And then lastly, we're not only interested in rendering RGB frames, but we're also interested in collecting annotations. And for this, we were able to use shader programming to automatically collect a wide variety of additional metadata on top of the simple RGB frames. So synthetic data has a long history in computer vision, and even more so with the advent of deep learning, it has become certainly very popular to use video game engines to synthesize data. So one recent example is the Cynthia dataset. So this dataset created a virtual world using Unreal Engine, and it used this engine to generate training data for the task specifically of semantic segmentation. Another recent work is the work by Richter et al. So in this work, the researchers, they basically hacked the internals of a video game, in this case Grand Theft Auto. And so they used the renderings from the video game while it was being played to collect these renderings. And not just that, but they were able to also, with an understanding of what's being rendered, to collect semantic data as well. In our lab, we've also done recent work in this area, for example, by using virtual worlds to collect ground truth data from multi-object tracking. So in this case, the task is tracking vehicles, multiple vehicles at a time, in an uncalibrated setting. So what we wanted to address next was to move from creating virtual data for tracking to a much more challenging task, which is creating models for recognizing human actions in videos. So as you could imagine, generating virtual data of human actions implies an order of magnitude of increasing complexity. So humans are much more difficult to model than vehicles, as you might assume. We perform very non-rigid motion, as you can see here. We have very complex interactions with objects and with other people. And there is, of course, a very large diversity in terms of viewpoints and appearance. So for example, here you can see a selection of videos of people performing the action cartwheel, but visually they look extremely distinct from one another. So our challenge here was creating training videos, synthetic training videos for action classification, which are diverse, realistic, and also physically plausible. So our solution was to create a generative model of human action videos, and our solution, we called it procedural human action videos, or FAV. So here our videos were varied with respect to things like the environment, the phase of the day, the weather, and then different other characteristics of the videos. And then here you can see some of the synthetic data that we generated. And so what we did is we created a virtual world with different environments. For example, you have an outdoor environment, you have an indoor environment, for example, here. Then, of course, you have many different human models. So you have men, women, children, and then also different weather conditions. So you have things like rain, sunny, cloudy, etc. So one great advantage of this approach is that you not only collect RGB data, but you can collect data from many other modalities. For example, we not only collected for FAV RGB frames, but we collected information about depth, semantic segmentation on a per pixel basis, instance level segmentation, and also optical flow. So these, for a human to collect this data, takes basically an infeasible amount of time for data on the scale that we're interested in. One other point to note is that this data was extracted all at once using multiple render targets, which made it very efficient and very fast to collect the data. So very often you would have to collect RGB, depth, semantic segmentation, one after the other, which was quite a waste of time. But we managed to use MRT to collect them simultaneously. So I just described to you the synthetic data that we acquired. Now I'm going to describe a bit how we use it. So what we used it for is to train a video action recognition model, which was based on a two-stream architecture. So here you can see one instance of this model, which has two streams. One stream is RGB, and the other stream is flow. And then we have three different versions of the same model. What data are we inputting? So we're inputting two sources of data, one coming from the real world, meaning that people were annotating by hand a small collection of video clips. And then we also have the virtual data that we are generating using our game engine. So what we did is that for every mini batch that was used to train the model, we mixed in this mini batch video clips from both sources. Meaning, so we call this a mixed source mini batch. And with this mini batch of mixed data, We run it through the model, and then at the end of every stream, 2 tasks are being solved. So we have 2 training objectives. One objective is classifying the clips from the real-world data, and the other objective, so you see the 2 here, the other objective is classifying the clips from the virtual data. So why do we need to do this? This is because for many video action recognition data sets, there's not a complete intersection between the action classes. For example, there are some classes, such as smile, which are very difficult to animate. So we don't include every single action of interest in our virtual data. So at training time, we have these 2 loss functions, but of course, at testing time, we only are concerned with the results of the real-world task. So here I'm showing some quantitative results of video action classification using this approach. So here we're seeing results for 2 well-known data sets. And you can see that using our approach, which we call cool TSN, we have improvements compared to not using the virtual data. So the comparison that I'm making here is that we're training a model in one instance without using virtual data. And in the highlighted region, we see the results when virtual data is included in these mixed source batches. And you can see that particularly in the case of HMDB51, which is a fairly small data set, you see quite a large improvement when virtual data is improved. So this implies that our assumption holds, which is that when target data is limited, virtual data can really improve performance. So to conclude this segment, the problem we try to tackle is how to generate large-scale annotated and synthetic video clips for use for computer vision tasks. And the solution we found was to use modern gaming engines, which are quite accessible, real to virtual world cloning via using small amounts of real world data, and then shader programming in order to acquire the renderings of both the RGB frames and then also the associated annotations and metadata. So just to wrap up, I've described to you 3 projects that we tackled at Naval Labs Europe, each of which addressed data scarcity in different ways. The first was via domain adaptation from a source domain to a target domain. The second was via data cleaning of a raw data set with noisy annotations. And then the last method involves data synthesis for video action recognition tasks. Thank you.